Guys ready? Okay. Guys, can we keep it down, please? Okay. Sweet. Moving on to stoichiometry, right? Otherwise known as quantitative chem. So now, stoichiometry is basically now from when you started chemistry up until grade 9. All you learned about was if I add this to that, I get another product out. If I add this to that, I get this out, right? Which is more your qualitative chem, right? What product do I form when I add certain reactions together? Your quantitative chem now is more focused on how much do I get out. So if I add this much of this and this much of that, how much of the products do I get back? Okay? So now we have to introduce the concept of the mole, right? You're just going to redraw the diagram in your books on page 24. You guys can quickly go there. When you're there, give me a quick yay. Okay. Quickly tell me what a mole is.
Substance.
Not the
Amount
element.
of something.
Carbon 12.
Carbon 12, yeah.
Carbon 12 is not a mole.
No, but it's the amount of carbon 12 in a mole.
Come on, what's a mole? Okay, don't give me the technical answer. In your understanding, what does, ladies, can we keep it down there? Now, what role does the mole play in what we do?
Measuring amounts of substance.
Okay, just look at it this way. If I go and I grab my drink quickly, right? This is not product placement for Woolies. Okay, if I grab my drink and I say, hey, I've got 500, imagine this is water. I've got 500 milliliters of water. And I say, Dylan, please take my 500 milliliters of water. He can say, oh yes, thank you. I will take your half a kilogram of water. And then Mike's like, but what do you mean? That's not half a kilogram of water. It's half a deciliter cubed of water, or something like that. And we can use all different values to describe what this thing is, but we didn't know how to really link it all together. So we got that okie over there, right? So now, just the long and short of it all, we can now take a given mass, and we can now directly convert that to a particular volume. And we can take that and convert it to the number of particles in our substance or matter or whatever it is we're dealing with. Yes? Okay, cool. So now, in this case, who's been on the how train? Okay, and who's heard the how train analogy? And I should see like 500 hands up now.
Pardon?
Who's heard the how train analogy?
You told me it once.
Okay.
I can't explain it.
You guys will all know it now. So now imagine on the how train, right? If I'm in Rosebank and I want to get to the airport, right? I'm gonna hop on the train at Rosebank, and then where am I gonna go first? And then
In the airport.
someone said it.
Marlborough.
Yeah, Marlborough, and then I'm gonna connect to the airport, right? From the airport to go to Pretoria, how do you get there?
To go back to the center.
Yeah, so you have to go from the airport back to Marlborough, and then you can go to Pretoria. From Pretoria to Rosebank, I'm going to go from Pretoria, have to pass through Marlborough to get to Rosebank. Yes? Okay. Similar concept happens here, where you're going to go from mass, take a train to moles, from moles take a train to particles, or from particles take a train to moles, from moles take a train to volume. Right? So now, different trains do different venues. Okay, so from mass to moles, I've got one train. It's the train of n is equal to m divided by my relative molecular mass. That is my mass in grams. From particles to moles, I've got the train of n is equal to n divided by Na. That's Avogadro's number. 6,02 times 10 to the 23. Which, incidentally, is the number of elementary particles in 1 mole of a substance. Yeah? Okay. And then, from, let's say, particles to volume, I take the same train back to moles. From moles, take the new train, n is equal to V over Vm. What's Vm? Vm is my volume of any gas at STP. Yeah? Which is?
22,4.
22,4 units. Alright, deciliters cubed. Yeah? You guys with me? Okay. Okay, so converting from any one of these to any other one, all I need to do is use my trains from each station. So I can't go from volume directly to mass. Got to first get the number of moles, then mass. From mass, got to first get moles, then particles, and vice versa. Okay, so whenever you get a stoichiometry, I keep pumping this board. Whenever you get a stoichiometry question, and you have no idea what to do, work out the moles of every value they've given you, and you'll get marks, trust me. Okay, but obviously when you leave here today, you should know exactly what to do for every single question. Now, let's take that and then look at what we call our mole ratios. Let's look at now if we had to create water, for example, right? So I'm going to reach into the cupboard, get some hydrogen. Hopefully you guys don't have hydrogen in your cupboards. Get some oxygen, put them all together, add a bit of energy, and then you end up with water. Is that balanced?
No.
Not. What am I missing? So I've got 2 oxygens there, 1 oxygen there, put a 2 there, now I've got 4 hydrogens, put a 2 there. Balanced, yeah? Okay, so now we've got 2, 1, 2. That's the mole ratio. So this is the ratio that my reactants will react in, right? So if I have 2 moles of hydrogen, they have to react with 1 mole of oxygen to produce 2 moles of water. Yes? Okay, cool. And this is how it should happen theoretically every single time. You guys with me? Okay, so let's take a quick example, right? If I have 1 gram of hydrogen, how much water can I produce? So 1 gram of hydrogen, how many moles is that? That's M over M, that's going to be 1 divided by 2, because it's H2, that's 0.5 moles, right? Mole ratio, that's 2:2, meaning I'll produce 0.5 moles of water as well, right? So I've got 0.5 moles of water. And then if the question was, what volume of water could I produce? Then I say my number of moles is equal to V divided by V at STP. Plug in the values. That's going to be 0.5, that's going to be 22.4, and I end up with my volume being 11.2 decimeters cubed of water. Simple enough, right? Okay. So now, yeah.
You don't times it by the number in front, right?
Never. So the number in front, all we use these numbers for is for the mole ratio. For when we're actually calculating then, 2 of these produce 2 of those, it's a 1-to-1 ratio. 2 of these produce 1 of these, you have to react with 1 of these to produce 2 of those. Is that okay? So if I've got 1 mole of oxygen, I can produce 2 moles of water, and so on. Yeah? Okay. But now, in reality, things aren't always perfect. Right? Like I always say, whenever you're sitting with friends, and it's always when you're sitting with 3 friends that one day you guys want to have pizza, but pizza only comes in 8 slices, and no one gets sort of an even number of slices. So then you have to get like an extra pizza because someone only got 2 slices and not 3. And you know the whole story, right? So now in reality, you never get things in perfect quantities. So I could give you 5 moles of hydrogen, and I could give you 2 grams of oxygen and ask you, how much water will I produce? Yes? So in that case, you must first figure out which one is the limiting reagent, because every single time there will be one factor that limits my reaction, and then I'll have something else that will be in excess. So you'll react them, 2 of these, 1 of those, 2 of these, 1 of those, 2 of these, 1 of those. At one point, I might just have no more of these to react, and still have these left, but I can't carry on. And the one that ran out first will limit my entire reaction. Yes? And the way to do that is to say, okay, well, if I react all of my hydrogen, how much oxygen will I need for that? Work it out. So let's say if I've got 4 moles of hydrogen, I will need 2 moles of oxygen. Yes? But what if I only had 1 mole of oxygen? That means I don't have enough oxygen for my reaction to take place fully with the hydrogen. Therefore, oxygen is my limiting reagent. And your hydrogen is said to be in excess. And then to work out your resultants, not your resultants, thinking mechanics. To work out your results and your product, you're going to use the one that was limiting, because that will determine exactly how much you'll produce at the end. Yes? I see a lot of blank faces. Okay, let's do an example so it makes more sense. Can I raise the board? Fantastic. Okay, on page 24, you guys look down there. I'm going to do example question number 2. Yes? Okay. So we have iron and sulfur producing iron sulfate. Sulfide, sorry, sulfate. Iron sulfide. So we got is that balanced? Is that balanced? Okay. It's 1 to 1 to 1. One of this will react with one of those to produce one of those in terms of moles. Yes? Okay. Calculate which of the two substances will be used up if 20 grams of iron and 10 grams of sulfur are mixed and heated. So I've got 20 grams of that, 10 grams of that. How many moles is that? Let's find out. M is equal to M divided by capital M. That's going to be 20. What's the relative molecular mass of iron? They're on your table. Periodic tables are on your table.
56.
56. Sure. Okay. Then we have 56, and then what's that as a decimal? Answer? Zero comma 36. Okay. Got 0.36 moles of that. So let's look at sulfur then. How many moles of sulfur do we have? We're going to apply the same equation. We're going to end up with 10 divided by, what's the relative molecular mass of sulfur?
32.
Come again?
32.
Okay. How many moles is that?
0.31.
0.31.
Yeah.
Okay. So they have to react in a 1-to-1 ratio. So if I were to react all of my iron, I would need 0.36 moles of sulfur as well. Do I have 0.36 moles of sulfur?
No.
No, I don't. Therefore, sulfur is limiting. Sulfur is limiting. And this is in excess. Yes? If I were to react all of my iron, my whole 0.36 moles, okay? How many moles of sulfur would I need? So I'm going to go divide by 1 times 1. I would need 0.36 moles of sulfur for my reaction to go by completely. Yes? Okay, cool. Sweet. Then the next question is B. How many grams of the other substance were in excess? So now, obviously now our iron is in excess, yes? So, yes?
Yeah.
Okay, someone said no. So then we only reacted 0.31 moles of this. So meaning, so number of moles left would be 0.36 minus 0.31. Can you guys see at the back? Okay. And that would give us 0.05 moles. That's how many moles now are in excess. How many grams is that? Then if we can simply just say my mass is going to be equal to my relative molecular mass times the number of moles. That'll give us 0.05 times 56. Come again? 2.8 grams. 56, that gives me 2.8 grams. Fantastic. Does that make sense?
Yes.
Okay, you guys have 7 minutes to do the activity question 2, and then if you're done with 2, you can do number 1. Yes? Yeah. Okay. Remember the question says, how many grams of the other one is in excess? First question was, which one gets used up first? So our sulfur gets used up first, it's the limiting reagent, right? So how many grams of my iron will be left over? So if this is my limiting reagent, I can only react 0.31 moles of that. Meaning, I'll only react as a 1-to-1, 0.31 moles of my iron as well. Does that make sense? So then how much is left? It's going to be 0.36, which is what I had, minus 0.31, which is what I reacted. And then I've got 0.05 moles left over. Right? And then I want to find the number of the mass in grams, and I plug in now my equation, and then I end up with my mass in grams. This is the other substance. Remember they first asked about which one is limiting? That's my sulfur. Meaning my other substance is going to be my iron.
Yeah, so how why did you minus
The 0.31. Because this is how much I can react with myself as the limiting one. So using my mole ratio, if I react 0.31 moles of sulfur, right? It's a 1-to-1 ratio. That means I'm going to use up 0.31 moles of iron as well in my reaction.
So are you using it because it's a limiting or just because it's a 1-to-1 ratio?
Both of them. I'm using it because it's limiting. I have to now work out how many of the other one I did use, and then limiting reagent, check my ratio, and then you end up with the fact that I used this much of the iron as well. Therefore, how much is left? 0.36 minus 0.31.
So what would you do if it wasn't a 1-to-1 ratio?
So if it wasn't 1-to-1 ratio, so let's say that was 2-to-1 ratio, right? Meaning I would have to react twice as much iron as I did my sulfur, right? So now I just say, well, 0.31 times 2, and I get my answer, and then minus that from the original amount. Does that make sense? Fantastic. If you guys need any help, Rob's there, Dylan's here, I'm here, and the social quickly. Cool, what's up? Yeah, that's just the number of moles. Remember, different atoms are different sizes. Different sizes.
Oh, like trying to convert it to moles.
Yes.
And you do the one that you use the ratios, the